let's see what we got here. It's going to be maximize subarrays after removing one conflicting pair. It's going to be hard. You're given an integer n which represents an array nums containing the numbers 1 to n in order. Additionally, you're given a 2D array conflicting pairs, where the ith conflicting pair is a comma b, indicating that a and b form a conflicting pair. Remove exactly one element from conflicting pairs. Afterward, count the number of non-empty subarrays which do not contain both a and b for any remaining conflicting pair ab. Return the maximum number of subarrays possible after removing exactly one conflicting pair. Alright, so let's see the first example here. If you have n is 4, so that means you should have an array that's 1 to 4. And you have conflicting pairs 2, 3, and 1, 4. You can remove one of these entries. So if you remove 2, 3, your conflicting pairs is now just 1, 4. And then there's 9 subarrays where 1 and 4 do not pair together. Those being 1, 2, 3, 4, 1, 2, 2, 3, 3, 4, 1, 2, 3, 1, 2, 3, 4. So I mean, if you have 4 elements, the number of subarrays that you can form would be 4 plus 3 plus 2 plus 1, because that's the size. You can think of it as 4 1-element subarrays, 3 2-element subarrays, 2 3-element subarrays, and 1 4-element subarray. And of those, there's exactly one that is inclusive of 1 and 4. So therefore, there's 9 remaining subarrays. If you remove the 1, 4 as from the conflicting pairs array, then you have a 2, 3. And there's more subarrays that contain 2 and 3 rather than 1, 4. So, okay. And then if n is 5, then you have 1 through 5. The conflicting pairs are 1, 2, 2, 5, and 3, 5. So there's at most 15 subarrays if you didn't have any conflicting pairs. And then here they say for you to remove 1, 2, leaving 2, 5, 3, 5. So if you have those, of the 15 possible subarrays, I think all 5, 1 through 5, 2 to 5, and 3 to 5 are the only subarrays that would conflict, and any other subarrays would be non-conflicting, so 15 minus 3 conflicting subarrays would be 12. Alright, so I think what I can, and here n is 10 to the 5th, so 10 to the 5th means that you can't do an n squared algorithm. That'd be 10 to the 10th. But it's likely, it's possible to do like a n log n or a linear algorithm. Almost certainly this is going to be n log n. You're pretty sure you want to sort the conflicting pairs. Alright, so I think here this seems like a sliding window one in some form or fashion. So if you start with counting the number of valid subarrays, this is non-conflicting, and no removal of any pair, of any conflicting pair. Then this should probably be using a sliding window. So the sliding window would be, you have a right index to your window, and typically the right index will have, if you have a valid window that has no conflicting pairs, the right index should be around, should equal the number of subarrays that end with that index on the right. So for instance, if the right index is 5, then the number of subarrays that ends with 5 would be like 1 to 5, 2 to 5, 3 to 5, 4 to 5, and 5 to 5. And then of those, you want to eliminate the windows that are conflicting in some fashion. The conflicting windows would be ones where the end index of the window, or end index, the bigger pair value would be less than your right index, less than or equal to your right index, and the smaller value, okay, so say the right index is 5, so in theory 5 possible subarrays that end at 5, like 1, 5, 2, 5, dot 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 5, 5 inclusive. And then exclude any window where a conflicting pair, AB, has B less than or equal to 5 and I guess it could be B and A is less than the left side. A is exclude any window where A is less than or equal to the left side. So for instance, if I have a conflicting pair that is, say, 2, 4, then it should be possible to do 3, 5, 4, 5. But if I do 2, 5, actually I think it might be the other way around. I think this is left is less than or equal to A. Yeah. And so if I have, so example here is if a conflicting pair is 2, 4, then if you stretch it all the way to 5, 5 can do 5, 5, 4, 5, 3, 5. You can't do 2, 5, you can't do 1, 5 because those would have 2, 4 within it. So excludes 1, 5 and 2, 5. The left side of the window is less than or equal to the A because then, yeah, then that window would be inclusive of both. Okay. Okay, so I think that's, and if there were more conflicting pairs, let's say there was a 2-4 pair and there was like a 1-3 pair, the 1-3 pair you can ignore because that restriction is strictly less prohibitive than the 2-4 pair. So I think you just need to worry about the earliest. So I think you consider every conflicting pair where the largest number is less than or equal to the right index. But then once that condition is true, then the restriction is then based on the lower number of the conflicting pair. So I think that seems like maybe. So let's go ahead and do it. So the answer is equal to the right, or the answer equals 0, and the right index is equal to 0, I think. No, the left index is equal to 0. So for every right index in the range of n, I need to sort this stuff. No, this is, yeah, okay, sort it. Conflicting pairs dot sort. Here would be open the window, restrict, count, open the window. So let's say the value is equal to, well, no, right? It's an ordered array, 1 to n, so I know the value is going to be just n plus 1, or right plus 1. So I think conflicting pairs need to sort based on the second index, I think. Needs to sort based on the b value and the a value. I think there should be lambda key is equal to lambda x, where x is based on the reverse of the values. So x0, x1, x0. Just go ahead and print that out. So if you have a tuple x, where the tuple is, well, not, I guess it's not a tuple, but a two value array, you're sorting based on the bigger value and then the smaller value. Let me do a test case here. Make sure that syntax is correct. Let's add something that will go between here, I guess. Actually, let's do 2, 5, 3, 5, 2, 5, and then 2, 4. This is gonna crash. Okay, so 1, 4, 2, 4, or 1, 2, 2, 4, 2, 5, 5. Okay, that's what I want. So I want to be looking at the second value to determine whether or not it should be considered as conflicting first. So I need an index for the compare that I am looking at. So I'll say this is the pair index. Pin is equal to 0. Okay, so this should be while, let's see, I think I also need another thing for the left restriction. I think it left conflict is going to be, I think maybe -1 to start. So while pin is less than the number of conflicting pairs, which is going to be pnum, length of conflicting pairs, while pin is less than the number of conflicting pairs and the conflicting pairs, the second value of it is less than or equal to, it should probably just be equal to, but less than or equal to the right index. And then pin should increment at some point. And the left conflict should equal the maximum of the left conflict index value and the pair's left side value, the pair's earlier value. Okay, so if there was a tie, like the window went to index 5, it should be looking at using 3 as where it should not, between 2 and 3, it should use 3 as the thing that conflicts. Okay. And then at this point, your answer would, the valid number of windows that end with 5 or within the right index would be something like the right minus the left conflict, I would say. So if it's 5, and there's a 2, 4, it would be 5 minus 2 approximately. So the issue here is the indexing. So the right represents, the value at the right is actually right plus 1. Value at the right is right plus 1. I think this is correct. Value right, so if it's 5, then the right is actually 4, and then 4 minus the left value in the pair would be 2, which is 2. Okay. And then answer increments by the valid. I'll probably just make answer plus equals this, but valid windows. Okay. Let's go ahead and print out the answer, or return the answer for the time being. And I'm going to, let's just run this, see if it checks out correctly. So probably should check this one. Probably do the little math here. There should be 15, and of those 15, the things that include 2, 5, and 3, 5 would be 3, 5, 2, 5, 1, 5, so that's 3. And then things that include 1, 2 would be 1, 2, 1, 3, 1, 4, 1, 5. 1, 5 is already done, so this one does 3, so 3 plus 3 is 6, so 15 minus 6 is 9. I think this is right. Okay. Okay, and then the next bit is to identify how removing one conflict would possibly change it. So conflicts. So if I were to keep track of the pair that results in certain conflicts, okay. So secondly is track, I guess, like track kind of top 2 conflicts, i.e. 2 restrictions, such that if the earliest restriction is removed, how many additional subarrays are valid until the second restriction applies, and the count of additional valid subarrays is the benefit of removing that restriction from the set of conflicting pairs. So it's like an opportunity. Is it opportunity cost? It's not opportunity cost, no, but yeah, I guess it is kind of opportunity cost. So for each pair that you remove, there might be some you will create possibly more valid subarrays until kind of the next restriction. So let's say the right index is 5, and there's a conflicting pair at 2, 4, another conflicting pair at 1, 3. So if you remove the 2, 4, it maybe makes valid 3, 5, 2, 5, but then the 1, 3 would prevent having a 1, 5. So the benefit of removing 2, 4 would be the additional 2, 5 as a possible subarray. And to maximize the valid subarrays, identify the restriction that has the most additional pair if removed. Yeah, so I think what I can do here is, so I think I need to keep a heap, where the heap is just a size 2 heap. Keeps size 2 heap of kind of the most restrictive, the 2 most restrictive conflicts, and track how many valid subarrays is possible based on any pair being the most restrictive. So if I have, let's say, pair 1 versus pair 2, every time pair 2 is the most restrictive compared to pair 1, if I have a count for the number of valid subarrays that are generated when pair 2 is removed and pair 1 applies, then for every pair 2 in the array, yeah, I can keep track of that count. So I think here I need to have an array of based on the number of conflicting pairs. So let's say the pin is the conflict pair index. The left conflict is -1. That's fine. And I have the extra valid, the kind of extras created, which is 0 times the number of, this is count of valid subarrays. Count of extra valid subarrays if pair conflicting pair I is removed, or if ith pair is removed. Okay. At that point, I need to have a heap. Which is going to be the top 2 remaining conflicting pairs. I think it should just start with, it should start empty. Heap of 2 most restrictive pairs. And I think this should be a tuple of the A value, the left value of the pair lower bound, low bound, comma, pair index in the array. The pen is necessary to keep track of where the extras to change. Okay. So I think here, while going through every pair that's in conflict for this right, I need to do something like heap dot append, no, sorry, heap push. Actually, maybe I can do heap push pop. I guess heap push pop. Heap queue, heap push pop. So I think maybe this is going to be if the heap is less than 2, or if the heap, yeah, if the length of the heap is less than 2. Ooh, I can be a little tricky. I can make two dummy values in the heap to go around this. All right, I'll do the straightforward way first, and then I'll do the tricky way afterwards. Heap dot push the tuple that is the lower bound, which is conflicting pairs. Oh, oops, this should be before the pin increases. Conflicting pair for this pin, the lower bound is 0, and then the pin itself, else heap. No, this is not how you do heap push. Heap push is a method where you call it on the name of the heap. Okay, and then this is going to be heap push pop onto the heap, the conflicting pairs for this pin, 0, pin. Okay. So the top element of the heap should be the less restrictive less restrictive conflict pair, and the second one should be more restrictive because it's a bigger index. Okay, and then the valid would be right minus so it'd be top. It'd be not the top of the heap, it'd be last of the heap. Only the top of the heap is shown. Fuck. I guess I could always do. I guess I should be still able to do -1. Yeah, -1 should still work. Conflicting pairs at -1. Because I know that heap should always. Okay, actually there could be an empty heap at the moment. If not heap, then the valid is just going to be the right. So if the valid's 1, then it's going from 0, 0. So it's 1. Yeah. If there is a heap, then the valid is equal to right minus the last pair, and then the 0 of that, which is the left bound. And then I'll say the do I need another if statement here? Maybe. Extras of removing this restriction, where this restriction is conflicting pair. Okay, so extras, this restriction, conflicting pairs at index is the first or the second element, that tuple plus equals, so how much can you get? So the benefit of removing this restriction, benefit is going to be something like extras, no, it would be conflicting, wow, wait, I forgot to use the heap here. Oh, this should be the heap. Heap at -1, 0. Yeah. This should be something like heap at -1, 0, minus. So benefit heap of -1, 0 minus like heap of 0, 0. Yeah, so the outermost restriction minus the innermost restriction. The difference between that, between the left bounds of them. But it could be that the outermost, there might be not enough, I guess. So I think maybe I'm just going to do the hack here. So I'm going to create 2 dummy heaps, or 2 dummy restrictions. And I'll say the 2 dummy ones are -1, and the pin for that would be pin, I guess. -1 pin. I'll need to create the extras array using 1 extra index for the dummy. Should be -1 or should be 0? If the restriction was based on 1, if the left index was 1, then that would equate to being 0. So maybe these should be 0 themselves. So if you have something that is restricted of 1, that would bump this thing off. And if you remove that restriction, 1 minus 0 is 1, so there's an extra benefit of 1. Okay, I think that's right. Okay, so at that point, I don't think I need this, because the length of the heap is always going to be at least 2, or exactly 2, if I do p push pop. And extras, this should always work because there's always going to be 2. And extras of conflicting pairs plus equals the benefit. And then the benefit of removing this particular, actually that's still fine. So also I can remove this not heap thing because the heap is always going to have something. Okay. So the valid's going to be right heap at -1. So if it's empty, or if it's just the dummy stuff, that'd be 0. If the right is 1, that'd be 1 minus 0. So everything's valid. Yeah, and then the benefit of removing that would be 0 minus 0, which is 0, so there's 0 benefit of doing that. Do I even need the extra pin? Because the pin, that thing never gets... No, I do. So I might still index into that spot. To extras, conflicting pairs. I think this is wrong. This should be using the heap. What am I doing? Extras, heap, that's the pin. Okay. And then the answer is incremented by the valid each time. Yeah, and then I'm going to return the answer plus the maximum extra benefit for removing any single one. No, it should be extras. Okay. Something's being done, even if it's not perfect, even if it's not correct. Every right index. Okay, let's go ahead and print out the right index and the current heap. Does this iterate to the end correctly? I think so. Okay, so let's go print out here and print out the extras here. Okay, so index 1 basically, or right is 1, 2, 3, 4. So when right is 1, there's no conflict. 2, right is 3. Oh. That doesn't seem quite right to me. And right is 3. And right is 2. While pen is less than pnum in conflicting pairs. Oh, I see. Or I see. Conflicting pairs of the pen. Is less than equal to right. Should just be less than. 2, 3. So 3, the right index should be 0, 1, 2, 3. The right index should be, the right index, I think there should be -1, no? I wonder why that worked before in my head. Okay, this is closer to what I'm thinking of. Now it's further off. So the right side value is 1, 2, 3, 4. And the right side value is 3. That's when this comes into conflict, possibly. That's right. Okay. Alright, so that one comes into conflict. That one gets added to the heap. 2 is the lower bound, 0 is the index to count it. So if this thing was removed, it would be 2 extras at that point. And then it would be 3 extras at this point, so it's 3. 2 plus 3 is 2 plus 1 is 3. So that's 3 here. my output. So my original count is going to be oh, let's see. If I remove this one, the other one becomes the blockade. So is there actually, yeah, there is no benefit to removing this one. Is there any benefit to removing this one? Because it ends up being that I counted 0 for it. I guess the only subarray that would be removed from this one is 1 through 4, and 1 through 4 always being removed by 2 3, so there is no additional benefit for that, so that's my 0 here. But I guess I don't know why this is adding up to why it's not adding up. So the number of valids that I ended up getting was just 2, really? Huh. Because 2 plus 3 is 5. Okay, let me go ahead and print out the right and then the answer at this point. Got 1 here and 1 here, interesting. So when it's 0, 0, 0 is the right index. Okay, it should actually be -1 here, I think. 0 is the right index, yeah, okay. So still off by 1. So when you have indexes, right index is 0, 1 should be the valid, right index is 2, or right value is 2, valid should go up by 2, so it should be total answer is 3. And then right side is 3, 3, there's 2, 3. 2, 3 should actually have 3, 3 as a valid one. So it should have gone up to 4 here. Okay. So the right index is 2 here. I think that there's something off by 1 for this code. I think it should be right plus 1. Right minus c plus 1. Then that's going to change everything else off by 1. Okay, maybe this should be 0 and it should be plus 1 in the right minus left plus 1. Okay. Alright, so still a little confused as to the indexing part that I'm screwed up on, but it does seem to generally work. Okay, so this test case 10.5. Holy shit! Oh, yeah, this thing needs to just be sorted. So lambda x should just be the bigger one, comma the smaller one, as the way to sort it. I see. just assume that they sorted the conflicting pairs. But then I do need to change the actual thing. So I think I need to start by saying conflicting pairs is equal to I think it would be something like min of A, B, max of A, B for every A, B in conflicting pairs. So for every, actually I think maybe it's not tuple. For every 2-value element in conflicting pairs, make a tuple that is the sorted version of it. Okay, let's go ahead and just print that return. See if that works correctly. Okay, it didn't crash. I think it worked. Okay, so that part is fine. Okay. All right. Solution is a solution for hards. Am I fine with this? So I have my conflicting pairs. I go through. I guess I don't need left conflict anymore. Do I need left conflict? Yeah, I don't need this anymore. I think I used it. So remove this. I have my extras. I have my heap for every right index. I think. Okay, so what I can do about what I can do to make sure that I don't have to do this condition is create a dummy conflicting pairs. Yeah, I don't know if I feel like doing that. So if the right index, I wonder if I should just do right index from 1 to n plus 1. That'll probably just make things a lot easier. So that would just make this thing conflicting pairs less than equal to right, and right minus left. I think that's still correct. Heap push the tuple that is the left bound and the index of that. Increment the index of the conflicting pair. The valid indices, the valid stuff is from the right side to the left side. The benefit of removing this I can just do this. I could probably just remove the benefit and valid and just be plus equals. So like the valid answer plus equals this. And the extras for this particular conflicting pair is incremented by the difference Okay, I think this is all fine. Count of extra valid subarrays if ith pair is removed. Heap of two most restrictive pairs. Okay, I think this is it. Obviously, it's not super efficient compared to other people's solutions, but I think this is pretty darn satisfactory for me. Okay. So in summary, this is going to be use sliding window to keep track, to count the number of valid subarrays, keep track of two most restrictive conflicting pairs that apply to current window, where the window is defined based on its right index. Identify the number of valid subarrays based on right minus low bound of identify the number of valid subarrays that end at the right index or right value as equal to right minus left low bound of most restrictive pair, where if pair is AB, then B is less than or equal to right, and and left. A is less. The left side must be greater than or equal to A. Is it? No, left side is less than or equal to A. The left side must be greater than or equal to A. Depends on what I mean by what I'm trying to define here. If pairs A, B, B less than or equal to right, left is less than or equal to A, are invalid windows, or invalid subarrays. Identify the number of valid subarrays that end at the right value as equal to right minus low bound as and then identify the benefit of removing that most restrictive conflict. Restrictive conflict as the difference between its low bound and the next applied low bound. Keep track of that in an array. And then we'll return the number of valid subarrays plus the highest highest benefit for removing for any individual conflict to be removed. And this is basically part A, part B, part C, and part C is kind of the big one. This is the use a heap to keep track of the two restrictive. And I mean, it's hard to identify everything that I did here, but yeah, the heap has two dummy restrictions. If you have something that starts at 0 as the left bound, that doesn't really restrict anything. And then every time you see another conflict that is possible, which is the right indexes of that conflict pair is smaller than or equal to this current right index, where this right index is not 0 indexed, but 1 indexed. Then add it onto the heap, remove the kind of least restrictive one off the heap, so that's the push pop. The answer increments by the number of valid stuff, which is right indexed to the left side of the most restrictive one. The most restrictive one on the heap is actually the one at the last index in the heap, and the benefit of removing that restriction from the heap is the difference between the low bounds of the two restrictions on the heap. Okay, and then time complexity, this can be O of n log n to sort the restrictions based on the upper bound, of pair, and O of n to iterate over, actually n here is the, actually I'll say O of r log r to sort the r restrictions, to sort the restrictions based on the upper bound of the pair, where r equals number of restriction pairs, conflicting pairs, and O of n to iterate over the O of n, it's O of n and also O of r here, because you have to still iterate over the pairs. I guess it'd be O of kind of max of n plus r to iterate over every possible right index from 1 to n, and while iterating over restrictions as well. Ah, shucks. I guess it's n plus r log 2. Each time you do that, you need to, it's constant work to maintain a heap of size 2. Technically, the iteration over the technically it also iterates, it also does heap push pop on a heap size 2, which is constant work, I guess. If this was a bigger size heap, like, then I'd include that in the calculation. Basically, this can be O of I guess you need a heap O of 1 for maintaining the size 2 heap, and maybe O n if treating the conflicting pairs array that needs to be reworked to be sorted. So technically I could have done this in place maybe, rather than create a new array. But whatever. Okay. Cool beans.